We're now looking at exponential growth and decay. So this is a 2-unit topic. Okay, 2 units. So just write 2 units. So we know that, just looking at what you've seen in the past, exponential function looks like this. This is y equals e to the x. That would be an exponential growth type function. And e to the minus x looks like that. So they're going to be based on these functions that you already know. All right, but we're going to be replacing the x's with other things. So the exponential function has many practical applications. It's involved in natural examples of growth and decay, such as population growth, growth of bacteria in a culture. So we're saying that these things grow exponentially, all right, like fairly quickly. The rate of cooling of a body, that would be this type of graph going down as it's cooling. So that would be an exponential decay. The rate of change of pressure with altitude, the rate of decay of radioactive substances, all right, that would be that type of graph. So the way, instead of just having y equals e to the x, our exponential function here is going to be y equals ae to the kt. And that's known as the growth function. So it's always this format, y equals capital A e to the power of kt, where a and k are constants and y is a function of t, okay? In the normal y equals e to the x, y is a function of x. With the exponential functions that we're looking at, y is a function of t, okay? So basically the x is replaced with the kt. Okay, so that is because, for example, we're going to be sketching it like this. This would be y equals ae to the kt. Now, because t is time, we're not going to have this part of the exponential curve. Time starts at 0. This is the time axis. This is the y-axis. And when t is 0, you get e to the 0 is 1. This y value here will be a. Okay? So that's an exponential growth function. Okay? Y equals ae to the kt is the function. Okay? Y is a function of time t. Now, what we're going to do is differentiate. So if y equals ae to the kt, isn't the a the constant, so we don't differentiate that? Then dy dt, we keep the a out the front. How do you differentiate e to the, remember t now is like your x. It's like I'm differentiating e to the 2x. If you differentiate e to the 2x, what do you get? 2e to the 2x. So here I'm differentiating ae to the kt. I keep the a, and when I differentiate the e to the kt, I get k times e to the kt, because I'm differentiating with respect to t. Notice we like to put this k out the front, so the derivative is k capital A e to the kt. Now, we know that this ae to the kt is actually y, so therefore the derivative is k times y. Now, so therefore dy dt is equal to ky. Now, dy dt equals ky. If we just look at the exercise we did on rates of change, dy dt is the rate of change of y with respect to t. So if dy dt equals ky, when you studied proportion, I think back in year 10, it means that dy dt equals some constant times y. K is just a constant. That means that dy dt is proportional to y. I'll show you. You may have, like I might say, so if I say dy dt is proportional to, do you remember that symbol? Is proportional to y, then we can say dy dt equals some constant times y. Okay, the first thing there is a proportionality statement. Dy dt is proportional to y. What that means is, as y gets bigger, dy dt gets bigger. That's direct proportion. In other words, as y gets bigger here, if we're timing it by some constant, that's hopefully greater than 1. Well, whatever happens to y will happen to dy dt. If y goes up, dy dt goes up. If y goes down, dy dt goes down. All right? That's direct proportion. All right? So, in other words, the rate of change of y, dy dt is the rate of change of y, is proportional to y because it equals a constant times y. Now, for any practical situation where we know that the rate of change of y is proportional to the quantity. So if you're told that dy dt equals ky, this is what it's saying, then you're allowed to say, therefore, y equals ae to the kt. All right? Now, you'll see it when we do some examples. So if you're given that dy dt equals ky, you can say, well, therefore, y equals ae to the kt. That's what this is saying. For any practical situation where we know the rate of change of y is proportional to the quantity, in other words, dy dt equals ky, then the growth function is y equals ae to the kt. You might be asked to prove it sometimes as well. Now, if k is 0, we have an exponential growth function. Sorry, if k is greater than 0, in other words, if k is positive, we have an exponential growth situation. All right, here. The quantity is increasing. We have growth. But if k is less than 0, if I just said that this was the function, but what we're going to be doing, we're going to be putting a negative in front of the k. So if we've got e to the negative something, we've got exponential decay, not growth. Okay? So if k is less than 0, the quantity is decreasing. In other words, we have exponential decay. All right? Now, initially, and we've spoken about this before, if we look at the function y equals ae to the kt, if we substitute the initial time when t is 0, we get ae to the 0, which is a times 1, which is a. So when you look at this equation, y equals ae to the kt, the initial value of y is this a value at the front, and sometimes we write it as y0. So instead of writing y equals ae to the kt, you can sometimes see it written as y equals y sub 0, in other words, subscript 0, e to the kt. Or you can also see it written like this, n equals n sub 0, e to the kt. All right? Or you can see it written as y equals ae to the kt. The main thing is that the reason they're calling this sub 0 is because it's the initial amount at time 0. That's why they call it y equals y sub 0 e to the kt, or n equals n0 e to the kt. It's really good to use this way of doing it when you're told that the quantity is going to double over a certain period of time. All right? You might have n0 and 2n0 here, for example. All right? Okay, so what we've got, the exponential growth and decay formula is given as y equals y0 e to the kt, or y equals a e to the kt if you want, where y0 or a is the initial value of y, k is the growth or decay constant. Now, it's the growth constant if k is greater than 0, it's the decay constant if k is less than 0 for that particular population. And this is really important, that y equals y sub 0 e to the kt is the solution if you're given the information that dy dt equals ky. So if you're told the rate of change of y with respect to time equals a constant times y, you're allowed to say, well, therefore, y equals y0 e to the kt. So the notation nt is often used to denote the value of n at time t. So sometimes you can see, you know, in this equation here, n, they might just say nt. It's the value of n at time t. n0 is the value of n when time is 0. All right? So page 2, we're just going to look at a couple of simple examples first, and then we'll get to some harder ones. The number of bacteria in a culture is given by n equals n sub 0 e to the 0.1 t. This is obviously exponential growth, not decay. Where t is in hours, make sure you look at the units. Initially, the culture population was 240,000. In other words, when t is 0, n is 240,000, or n sub 0 is, what's n sub 0? 240,000. Remember that n sub 0 is always the initial amount, all right? It says how many bacteria were present after 5 hours. Now here's the formula, n equals n sub 0 e to the 0.12 t. Look, they might say show that n sub 0 is 240,000. To show that, I'm just going to go You know how we've got m sub 0 is 24,000? I'm just going to show you how you would show it. You would say when t is 0, n is 240,000. So if you want to work out what n sub 0 is, you'd now use the formula. You'd go 240,000 equals n sub 0 e to the 0.12 times 0. So 240,000 equals n sub 0 times 1. So can you see how you get n sub 0 is 240,000 if you've been asked to show it? Okay, so n sub 0 is 240,000. So therefore the formula is now n equals 240,000 e to the 0.12 t. When t is 5, n is 240,000 times e to the 0.12 times 5. 0.12 times 5 I think is 0.6. But just go e bracket 0.12 times 5 or work it out and then do it as one value. Just don't put 60 or 6, you know. No, you can put 0.6. I'm just saying don't mess it up. 0.12 times 5, make sure you get it right with your decimal places. What do we get? Hopefully you get this number. Do you? Done it on your calculator? 437,000 bacteria after 5 hours. 2. The number of people in a town is given by n equals 12,000 e to the 0.9 t, where t is the number of years since 1980. So with this type of question, you've got it, time equals 0 is 1980. They're asking what's the initial population. I know that you can see it there already. What is the initial population?
1,200.
It's 12,000. So when t is 0, n is, look here, e to the 0 is 1, n is 12,000. Okay, when t, now part B says what would be the expected population in 2000? How many years is that? When t is 20. N is 12,000, so these are very straightforward so far. E to the 0.9 times 20, which is 7.88 times, girls, this is exponential, goes up very quickly, so 20 years, okay? Ultimately, I don't know, that'll do 7.88 times 10 to the power of 11, pretty big. Okay, next one, question 3. A ship is travelling at 6 metres per second. Now, metres per second, they're giving you a rate this time, okay? That's the rate of change of, well, that's its speed. Sorry, girls. A ship is travelling at 6 metres per second when its motors are stopped, okay? The rate of change of its speed is proportional to its speed. So rate of change of its speed is ds dt is proportional to its speed. When you're given a statement like that, you write ds dt equals a constant times the speed. And after 100 seconds, its speed is 3 metres a second. So it's a ship. It's travelling at 6 metres per second. They turn the motors off. Do you think it's going to keep moving, this ship? Yes. All right, so it'll keep moving. That's why after 100 seconds, it's slowed down from 6 metres per second to 3 metres per second. All right? Now, in other words, do you think this is exponential growth or decay? Is the quantity or value going up or down? Down. So notice here, we'll get to this eventually, but k is negative. You'll have e to some negative value times t. All right? So the question is, so it says after 100 seconds, the speed is 3 metres per second. The question is to find when the speed will be 1 metre per second. It's obviously going to be after 100 seconds, right? So this is the information you're given, that ds dt equals ks. Remember how I said that if you're given that information, you're allowed to now say, well, s equals s sub 0 e to the kt. All right? Now, if you don't know to write that, you're stuck, okay? So when t is 0, s is 6. So we can substitute t is 0 here, s is 6, and you know that we're going to get s sub 0 is 6 because that's always the initial speed. So in other words, s equals 6 e to the kt. We're then told more information that when t is 100 seconds, s is 3. Just making sure our units are correct. 6 meters per second, 100 seconds, meters per second, it's all good. So when t is 100, s is 3. So 3 equals 6, e to the k times 100 here. 3 divided by 6 is a half, equals e to the 100k. Taking logs to the base e of both sides, we've got ln 0.5 equals 100k. So therefore k is going to be ln 0.5 over 100. Girls, you know the log of anything between 0 and 1 is negative. ln of a fraction between 0 and 1 is negative. So that'll be negative over 100. We get negative 0.0069314. So what happens is, therefore, this is our new equation. S equals 6e to the negative 0.0069314 times t. That's your new equation for S. So often the questions will say find S sub 0, find the value of k, hence find whatever. All right? So now we can answer the question, find the speed, find when its speed is 1 meter per second. So when S is 1, we put 1 equals 6e to the negative k value times t. Dividing by 6, 1 over 6 is e to the negative that value times t. Taking log to the base e of both sides, we've got ln 1/6 equals negative 0.0069314 t. So t is just ln 1/6 divided by that value of k, which is 258 seconds. So therefore, the speed will reach, and that's now rounded just to the nearest second, it'll reach 1 meter per second after approximately 258 seconds. Notice it's slowing down. It's slowing down. Slows down quite. Because look, exponential curve looks like this. Okay, now, according to this model, the ship's never going to stop. Okay, but it will. Okay, but according to the model, the ship will never stop. And this value, if we were graphing it, would be 6 meters per second. That would be the speed. That's time.